Hey guys, welcome to another video. So today we're starting a new topic in the Extension 2 syllabus, and one of my favorites, integration with recurrence. So if you have seen as many past papers as I have in the Extension 2 syllabus, you'll find that there's one of these in every paper, right? Like it's a staple. Well, I say every, okay, most papers, right? Like 99% of papers. It's a staple in most papers, and it's about 4 to 6 marks per paper. So, like if you can't do this, you just shot yourself in the foot, right? So make sure you're on top of integration with recurrence. Now, integration with recurrence relies on integration by parts for most questions. Some questions don't, but they're rare. So I guess what I'm trying to say is integration by parts. If you don't know how to do that, please learn that or hit up the videos that I've already put up on integration by parts. There's a cool little strategy that my class has started using called the DI method, so much faster. So if you don't know what I'm talking about, DI method, there's a video up there on the channel. Go check it out. It's amazing, especially for ones that are really repetitive in terms of recurrence. Have a go. Now, so today, the recurrence questions that I'm going to do generally has two parts. First part, we prove a recurrence statement. Second part, we use the recurrence statement. So before I go there, let's start with putting up the acronym used for by parts, right? So integration with recurrence. All right. Now, it still surprises me when teachers, when students tell me that teachers at school don't teach them integration by parts using the acronym of LIATE. LIATE, very quick way of helping students identify the function for you, right? In this formula here. So the formula that I'm talking about is if you integrate any function of u dv, that's the product rule in reverse minus integral of v du, right? Have I got that the other way around? No, that's right. Yeah. So in this case, that is the integration statement. So sometimes I have the tendency of swapping the v's and u's around. Now, in this case here, right, if that's the formula at play for integration by parts, you can see, I'll use a different color here, right? There is one function for u and another for dv, right? LIATE is a cool little acronym, right? And I'll write it with a bit of space because they all sort of stand for something, right? That lets you identify the function for u. So LIATE, that's like logs, inverse functions, algebra, including one as trig, and that's exponentials, right? So given an expression with two functions, right? Let's say I have logs and trig. I would let u be logs first, reading from left to right, right? And if there's algebra and exponential, let u be algebra instead of exponentials. Now, and I'll say this I've got 4 questions prepared today. The third and the fourth one, LIATE really doesn't work, right? And when it doesn't work, you need to really understand, and this is where, okay, teachers that teach LIATE, great, right? That's like the least, I guess, they can do. What teachers then don't tend to talk about is why LIATE was created, right? Or what's the deal with LIATE? LIATE is an acronym that basically orders things that you should differentiate, because that's what u is, right? You differentiate u and you integrate dv. What they really should tell you, right, in addition, is LIATE, there's a bit of a misconception. LIATE, it's not, when you're selecting between two functions, it's not actually selecting which one you should differentiate. It's actually selecting the one that you shouldn't integrate. And I'll explain. Because if you think about it, right, if you let u be logs first, you can differentiate logs, but it's quite difficult sometimes to integrate logs, right? So basically you reserve sorry, let me say it again. You let u be logs because you can differentiate it, right? So as opposed to letting dv be logs because it's hard to integrate. So sometimes you got to ask yourself the question, when LIATE fails, right? you're going to have to ask yourself the question, which one do I not want to integrate? Because that's what I'm going to differentiate now. With that sort of principle in mind, let's start some questions, and I'll deal with that notion where LIATE fails in question number 3. So let's proceed. This question from James Roos, now a bit of a misdirection here. James Roos feels like a hard question, but this is actually probably the simplest recurrence question you can find, right? Or one of the simplest, where now for all sort of recurrence questions, I sort of define for you an integral with a subscript of n, right? And n in this case, right? Let me see if I can get the pink pen back up. So n's there, and n is in the integral itself. So what that means is anytime you sub in a value for n, that value of x to the power of changes, right? Now in this question, not really nice because I don't tell you what n is sort of bound by, but that's fine, right? I'm going to assume where n equals to 0, 1, 2, blah, 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 onwards, right? It's important to sort of know where n starts. All right, now look at this, guys. Classic recurrence question, right? 1, prove the recurrence relationship. In is related to in minus 1, and then evaluate I2, right? So find the value. So prove recurrence, use recurrence, right? So let's do this. So for part 1, we're defining an expression for integral of capital In to be with the limits of 0, 1, x, n, ex, right, dx. Now, applying LIATE, right? So in this case, we have algebra, right? And we have exponential. So quite simply, if you did LIATE, you'd go let u equals to a first to x to the power of n, right? Differentiate that. So then du equals to bring down the n minus 1 to the power dx. And then let dv be the other guy. So in this piece here, that there is u and that there is dv, right? Then dv would equal to ex dx. Now you can see, just to talk about the purpose of LIATE, it wasn't so much about this. For for xn and ex, it's actually both of them are easily integratable, but check this out, right? Ex is really easy to integrate because integrating that is just ex, right? So the exponential function is the easiest to integrate, so that's why it's pushed back on the LIATE for you, right? Cool, got my tools. So therefore, all right, in equals to, with limits, so uv, so xn ex with the limits of 1 and 0 minus integral of v du, right? So because I'm multiplying this, there's a constant there, so I'll bring the constant n out, limits of 0, 1, and it'll be x n minus 1 ex dx, right? Can I ask a favor? I'm just gonna make the n a little bit further out because I want to say, now, whenever you do an integration with the recurrence question, right, the purpose is this. The purpose, or sorry, when you're proving it, what you're aiming to do is basically find your original integral for in repeated with a different power of n. There it is, right? That looks exactly the same as my original. The only difference is that is n minus 1, which therefore makes this guy equal to I n minus 1. Does that make sense? So if everything else is equal, but the power or the n term is 1 less or 2 less, then replace that whole expression with I, in this case, n minus 1. Beautiful. So we're going to do 2 steps. Therefore, in equals to, now sub the limits in, first step. So that's 1 to the power of n, right? Don't need to know what n is, e to the power 1 minus 0 to the power of n, e to the power 0, right? Sorry, minus, that's n now times this new term of n minus 1. Guys, that's just e, right? Because the 0 goes away. Yeah, 0 goes away. So therefore, I've proven my recurrence statement, right? Is that all right? So what did I do there? Integration by parts. And then the moment I identified this blue box looking exactly the same as my original, but with n-1, replace it with the in-1 term. Once you do that, sub in your limits in this case, get the recurrence formula, get 2 marks, right? Very straightforward, right? Nothing too fancy about that. So, and then the classic question is, let's now use my integration statement. So I'm going to show you the way that, I've been taught. It's a bit tedious, but it's safe. Some teachers try to find shortcuts in this, and that's fine. If you're a big fan of shortcuts here, that's cool too. But the question says, can you please find the value of I2, right? I've always been taught, start with I2 and then constantly sub it into, right? So in this case, sub 2, right, into sub n equals to 2 into the recurrence statement, right? So let's see what we get. So when that's 2, it equals to e minus 2 times I, 2 minus 1, which is 1, all right? So there's my I2 depends on I1. So then I'm going to now go, okay, what if it was I1 then, right? I'm going to sub n equals to 1 into my recurrence formula. So you can see what I'm trying to do, right? I'm going to keep subbing these guys in, right? And that goes e minus 1 times I 0. Now, when you hit 0, and this is why the question wasn't really, was a bit poorly asked, they should define for you the first value of n that's possible, right? For this integration with recurrence statement. So I0 is where we stop, because once I0 is there, right? I'm going to just highlight this, right? Off to the side, I'm going to find it, right? So I0 is equal to, and this is where, go back to your original integral there and just replace the n with 0. And then you should have a very easily integratable statement, right? So that's the same as that's 0, ex is just ex, right? Pretty basic. And then 1, 0, guys, e to the power 1 minus 1, so e minus 1, right? Now that's important. So once you get the value of I0, it's a bit tedious because we said I2 equals to something I1, I1 equals to something I0, found I0. Now we're going to backwards populate to get the value of I2. So what I'm going to do is basically take this guy and then repopulate it back in here to get therefore, all right, I1 equals to e minus 1 lot of e minus 1. What's that, guys? Which is e minus e, that's just 1. And then I will take this guy, sorry, I'll use a different color here. Take this guy and then populate this guy here, right? So basically backwards populate, right? So therefore, I2 equals to e minus 2 lot of 1, right? And that's my answer. So that process feels tedious because we derive from I2 all the way down to I0 and then found I0 and then populated, but that's the process, right? Now, some teachers started doing this, right? They go, I want I2, I'm just gonna skip everything, go down to I0, find that, and then it's the same thing, right? It's the same thing. This one just shows all the working out. Guys, that's the first question on recurrence that I wanted to cover. Hopefully that's all right. Nothing too wow about that. Let's do another one in the easy bucket and then work up to a question that LIATE fails and is much harder. And just to give you a plan for this series, I'm planning to do about 3 videos. The first one's introducing the framework, which is what I always like to do. Second one, I want to do trig, right? Classic trig questions. And then the third one, let's do some hard ones, right? Because there are hard questions with recurrence, right? So let's aim for that. Three videos in this series. All right. Hills Grammar. Let's do another one. Now, can you see same structure? All right. They define for you IN, and in this case, let me just depict the. I'll just highlight the N there and the N there. Good. Yeah. Show recurrence statement and then prove or use. Now, in this one, they don't say find IN, but you can see in this one that expression there looks exactly the same as the original, but with a 3 there. So inadvertently, they've given you right? That guy there is I3. Does that make sense? Sometimes they give you the I, sometimes they just say, can you please find this integral? I mean, n is 3, so that's I3. So 5 marks. Let's do it. So part 1, all right, just like before. So we have an expression for in with the limits of 1 and e, x. Yeah, I'm just going to replace it with ln because I'm lazy. Power of n dx. All right, so that now LIATE kicks in. Just to be clear there, let's highlight this as well. That guy there is algebra. That is clearly a log expression, so I'm going to let that. Now, that makes a lot of sense, right? Because if I let u equal to the log, I can differentiate that using chain rule. If I let dv equal to the log, very hard to, in fact, I'm not sure how I can integrate that, right? That guy there is dv. So just said that. Let that be u, and then this guy and this guy together, right? Together, that's dv. So let u equal to the log statement of ln x to the power of n. So let's differentiate that, right? So du, bring down the n, ln x, n minus 1, and multiply by derivative of the inside. So that's 1 on x. So I'll divide it all by x, and then dx, right? Perfect. Let dv equal to x dx. So once again, the whole purpose of that, very easy to integrate x, very hard to integrate ln x, right? I keep talking about that as the reason for using LIATE, right? It's not very commonly discussed. To integrate that, pretty easy. So got my tools by parts. So therefore, right, in. Now what's my limits? 1 and e. Okay, cool. So uv, so be x squared ln x to the power of n over 2. The limits e1 minus. Now, let's see. I'm multiplying this with this to integrate, right? So anything constant, n and 2 are constant, so I'm going to bring those out first, right? N and 2 integral between 1 and e. And then what's left? I've got x squared and x cancelling out, right? So then it'd just be x ln x to the power n minus 1 dx. So looks scary when I multiply them together, but hey, look at that. Doesn't that, and I did this last time and I'll do it again. So let me put a blue box around my original, because guys, can you see that that looks exactly the same as my original? Now, sometimes a lot of questions, when you do once you do the by part stage, you'll get the blue box immediately, right? And that looks exactly the same as the original, but the only difference is n minus 1, right? And this is why it falls under the easy bucket, right? Because that there just gets replaced with n minus 1. The harder questions, you got to work for it. You got to work to produce something that looks like the original blue box, right? And this one is just there, right? Simplifying the algebra is just there. The next 2 questions, you got to work harder for it. And that's where there's worth in just seeing more questions, right? All right, so now it's just a matter of me subbing in my limits. Let's see, subbing e, ln e is 1, so that's like e squared ln e to the power of n on 2 minus, now that 1 squared, I know ln 1 is 0, so that goes away, perfect, minus n on 2 times n minus 1, right? So I know this guy goes away, and ln e is 1, right? So therefore, I've got my recurrence statement to be e squared on 2 minus n on 2 n minus 1. Quick look at, perfect, exactly what I want. So got my recurrence statement to sub in, right? Perfect, 3 marks there. Yeah, not too bad. You know, pretty straightforward, pretty stock standard. And then for part 2, right? Now in this question, does actually tell me positive integers, right? So that's important because n equals to 1, 2, 3, etc. So I can't go less than 1, right? Is that right? Positive integers. So Let me just big brain that. So, yep, okay. Positive integer. I was hoping I can use 0. The answer says I can use 0. Okay, you know what? Can I think the question says asked, sorry, incorrectly said positive integer. I think n can be 0 in this case. Yeah, because I'm looking at the answers and it definitely does say so. Well, let's not you know, try to work harder than we should for this. So now I3, right, is the question that they want. So I3 using the recurrence equals to e squared. So subbing n equals to 3 into the recurrence formula, e squared on 2 minus 3 on 2, I n minus 1, we'll use I2, right? Cool. So in this case, there's a 3, there's a 2, right? Depends on 2, so I'm going to now derive the formula for 2, right? And I know subbing it in, you get e squared on 2 minus 2 on 2, so that's 1, I 1, and then you keep going. It is a bit tedious, right? It is a bit tedious, but this is just the working out to ensure that I sub in the right stuff when I do it. So that's n minus n on 2, I 0. Now it's a bit cheeky. This question is asked, I think it's positive. It should say n greater than or equal to 0, right? Now, once I have I0, guys, I'm going to pause there off to the side, right? Off to the side, get the value for I0 by subbing in the limits and subbing in the 0 into the integral. So x times ln to the power of 0, so that's just x, right? And in this case, guys, x squared, that's x squared on 2 e1, so therefore it's e squared on 2 minus 1 on 2, right? And then what do I do? Once I get that value for the pink, I repopulate, right, to work back up to I3. So let's do that. So therefore, I1 equals to e squared on 2 minus a half, e squared on 2 minus a half. Right, there's a lot of halves here. Just making me work for it. So let's see, I'm just trying to make sure that I'm getting it right. So perfect. Yep. E squared on 2 minus e squared on 4. That's like a half minus a quarter. So that's e squared on 4 and then plus a quarter. Is that right? Check that. Perfect. Right. Guys, once you get that, right, I want that populating this guy here. So this guy into here, please. Therefore, it's tedious, right? It's just a bit of tedium. So let's see, minus 1 times, so just e squared on 4 plus quarter. How much space do I have? Not much. Okay, can I just anticipating might take a while. Yeah. So let's see. That's a half minus a quarter again to that e squared on 4 minus a quarter. Yeah. And then, guys, one more color there. That's I2, and then this guy goes into here. Yep. And then so therefore, let's see if I could do it zoomed out. I3 equals to e squared on 2 minus 3 on 2, e squared on 4 minus a quarter. Therefore, I3 equals to, what's that, e squared? Jesus, 3 on 8. What's a half minus 3? 1/8? Yep. E squared on 2. Oh, sorry, on 8. 1/8. And minus this guy times this guy, so plus 3 on 8. Yeah. Guys, that's my answer. So apart from the little bit of tedious repetition, right? Hopefully that's not too bad. That's how you do it, right? For 5 marks in a year 12 past paper, HSC, it's in every paper. So please make sure you understand the concept. That's a framework for doing these easy questions. Let's hit up a harder one where LIATE fails, right? All right, here's a classic. Now, 4th Street. So what do I have here? Let me zoom in a bit more. Once again, classic structure. There's my IN, right? Now, one thing to note, no limits, right? That's important. So no limits. Yeah. So I got to prove that and then find IN. Cool, right? Pretty straightforward. The only difference is that's +1, right? See that +1 there? Might be problematic. We'll have to think. All right, +1. All right, let's do this. So now, when you start this, right, and you start applying by parts off the bat, you start thinking about it and you go, I'm not sure even this one needs by parts, actually. So I kind of lied. Remember how I said that, let's see, it's true for the next one as well. That is true for the next one. What is it? Okay, sorry. Oh, no. I'm thinking about differentiation. I'm confusing myself. So this one you do by parts, and you can see. So let me put a 1 there and put the dx on the back. That this isn't LIATE friendly, if there is a term. Why isn't it LIATE friendly? There's only one function, right? There's only one function in this case where that guy there is algebra. There is no other function. So when there isn't, generally speaking, you multiply by 1 and that becomes your next function. But 1 is generally considered to be algebra as well. So in this case, you have a little bit of a conundrum, right? The conundrum is you got 2 functions that have the same categorization in LIATE. When that happens, I always say to my students, go back to the principle of LIATE. The principle of LIATE is you always let u equal to something, and you always let dv, right? dv equals to something else. The purpose of LIATE is to put the the harder function into u, because you can differentiate anything, and put the easier function in dv. So in this case, 1 dx is going to be my dv, and this guy is going to be my du. Yeah, that's what I'm going to do here. So let's see where that takes me, right? Now, by the way, sometimes it doesn't work and everything falls over. There's a classic question, HSC 2014, last question, 3 marks. Have a go at that for like an interesting by parts question where they don't give you any guidance and you have to use these principles to make it work, right? So let's see. I'll put this guy into downstairs. So in there. So therefore du equals to, now that's like power -1, -n. So when I differentiate, I bring down the minus n, and I go 1 plus x squared minus 1 to the power multiplied by, I'm just going to move this guy over, right, multiplied by 2x dx. Yep. And I'll clean this up slightly, so that equals to minus 2nx all over 1 plus x squared. Right, if that's minus, then it'll be n plus 1. Yeah. And then this guy here would be 1 dx. So when I integrate it, v equals x, right? Piece of cake. All right, got my tools. Let's perform the by parts. So therefore, in equals 2. I don't need limits, so it'd just be u times v. So x on 1 plus x squared is about it. Now, quick glance, and does that look like there? It sort of looks like it. There it is, right? So I feels like I'm on the right track. And then minus. Now, guys, I want this guy multiplied by this guy. First thing you note is, see that negative? So when I minus and I pull out the constant, so this guy becomes plus 2n integral, and it'll be this guy times this guy, so x squared on top on 1 plus x squared power n plus 1 dx. Now, remember how I said to you, what do I have to do now, right? See that blue box on the original, right? I want this guy to look the same, right? It doesn't. That's got x squared there, that doesn't. So in the previous question, the moment I did by parts, it was there, right? There was the recurrence was obvious, it was already there. In this case, it's not. So I need to work for it. Guys, how do I work for it? Generally speaking, if it's algebra, right? Like in this case, no trig, to work for it, you basically go, see how that's x squared and that's x squared? And there's a +1 there. So I'm going to +1 and simultaneously -1 to manipulate the top to make part of it look like the bottom, right? And then I'm going to split the fraction, right? So in this case, x on 1 plus x squared power n plus 2n. Guys, split this integral into 1 plus x squared over 1 plus x squared n plus 1 minus 1 plus x squared n plus 1 dx. Now, for those that know, right, the next steps are pretty straightforward in that this cancels out with the +1. What do you get? You get this guy, right, the integral of this guy, which is just 1 on, it looks exactly the same as the original with the same power of n. This guy is in. This looks exactly the same as the original as well, but with an n plus 1 power. So that is in plus 1. So then you've done it, right? By adding 1 and minusing 1 and splitting the fraction, you've created two versions of the original blue box. One looks exactly the same power. One's got +1. So then I can go, therefore, the in equals to x on 1 plus x squared to the power of n plus 2n bracket in minus in plus 1. Now, that looks still a bit different to this guy. What I'm aiming to do now is basically make in's the subject, right? So expand that, right? So using rainbows, just expand that times that, and then bring the 2n times in over to the left, factorize, make it the subject, right? So there's a bit of work left. So what I'm going to do is in here, that's 2n, so minus 2n times in, right, equals to x plus x squared. So minus, let me just check in the proof. Yep, oh, look, in the proof, they actually made this guy the subject, right? That's important as well. So let me expand it then. Let me continue, and then you'll see what I'm trying to do. Minus 2n times in plus 1, right? Guys, almost there. So what I'm going to do, I'm going to switch everything. I'm going to bring this guy over here. I'm going to factorize in and then bring it back over here, right? So I go, therefore, 2n. Sorry, I need to zoom in to write a bit neater. Okay, I don't have a lot of vertical space, so that's fine. 2n in plus 1 equals to x 1 plus x squared n, and then now factorize in, bring it over, so you sort of get like plus 2n minus 1 in, right? Because if you factorize 1 minus 2n, bring it over, negative, flips the sign, flips the order, yeah? And then therefore get rid of this guy, divide both sides by, let's see how the question wants me to express it, 1 on 2n, and then divide by 2n, perfect. So it just goes, therefore, in plus 1 equals to 1 on 2n times x on, put a little dot there for times 1 plus x squared to the power of n plus, and then 2n minus 1 outside of 2n times in, and that is my final proof. Right? So that one there is a little bit more hard, is a bit more difficult, right? Because you got to work for the proof, right? Not as straightforward as the ones before. Now, once you do that, guys, we need to then use that as part of our recurrence. So that's probably the easy part. In fact, can I just go over here? And I always say this to my students, right? If you can't do part 1, which is 3 marks, you still can do part 2, right? Part 2 is probably the easier part, where you go I3 equals to, sub in 3 to that whole expression. So you get 1 on 6 times x on, oh, sorry. So when n equals to 2, right? That's 3. So just to be clear, I sub that in wrong, right? So in this case, the recurrence is given in terms of n plus 1. So when it's I3, for this one, n equals to 2 only, right? Yeah, just to be clear about it. So actually it's 1 on 2 times 2 is 4 times x on 1 plus x squared to the power of 2, right? N is 2, right? Plus 3 on 4i2, right? Then for the next one, to get I2, that's like subbing in n equals to 1, right? Yeah, that's 1 on 2 times 1, so 2 times x 1 plus x squared to the power of 1 plus 2 minus 1, that's 1 on 2 I1. Now let's look at what n can be. N is non-negative, and I think in this one they actually mean non-negative, right? Not like the last one, right? So in this one, n equals to 1, 2, 3, etc. So 1 is where I stop. So that's a quick pause. I said this before, off to the side, right, guys? So integral of, there's no limits here, of dx, 1 plus x squared to the power of 1, right? So it's just 1 plus x squared. Now we all know that that is tan inverse, right? X plus c, right? So then once you get that, pop that back in, right? And then we start repopulating, right? Start repopulating, and you get, therefore, I2 equals to half x. So I'm trying to be really carefully, 1 plus x squared plus a half tan inverse, right? I'll put in the plus c at the end, right? Tan inverse of x. Is that right? Let me just check that. Perfect, right? Perfect. And now what do I want to do? I want to put this expression, I'll factorize a half out when I put it into, that's I2 into here, and I should have my final answer. Right, okay, let's see. So therefore, I3 equals to 1/4. I'm just writing quarter, I'll just write x on 4 times 1 plus x squared plus, guys, 3/4 times the half there. You'll see that it's like, what's that, 3 on 8 times this. So maybe I'll go 3x on 8, 1 plus x squared plus 3 on 8, tan inverse plus c. That's my answer. Quick check. Perfect. So that one there made you work a little bit harder. Guys, I said I'd do 4 questions. I'll probably leave this video here. Just to set the framework, showed you a question where LIATE fails, and maybe the one that I had prepared next, very similar here. Maybe I'll pop it into video 3 to start it off, where it is in the so-called harder bucket where LIATE fails. Hope you liked that video. The next video, I'm going to explore trig with recurrence, kind of different questions that you see, different approaches. Guys, tune in for that. If you like the video, please give us a like, subscribe, tell your friends, and I'll see you in the next video. See you later.